Hello class, welcome to this video on AP Statistics, Chapter 7, Lesson 3, Sample Means. So our essential question, how do we work with sampling distributions of means and difference of means? So this is what we're going to focus on the mean and the difference of means as we work with sampling distributions. So learning target 1, calculate the mean and standard deviation of the sampling distribution of a sample mean X bar and interpret the standard deviation. So first off, let's go ahead and define what we mean by the sampling distribution of the sample mean. So in this case, a sampling distribution of the sample mean x bar is the distribution of values taken by the sample mean x bar in all possible samples of the same size from the same population. Okay, here, let me zoom in on this portion here. Just focus on that part. Mrs. Gallow's penny activity for sample means of pennies and 50 samples of size n equals 5 and 50 samples of n equals 20. So what we want to notice is that in this activity for Mrs. Gallow's statistics class, they took samples of pennies. The one on the left is where they took 5 pennies at a time from a pile of pennies, and they did the sample mean of the ages of the pennies. And that's what you see here, the sample mean year. And notice that the distribution um, looks a little bit, skewed here, but on the right, it looks kind of symmetric, right? Almost like it wants to be a normal distribution. So I want you to realize that from n equals 5 to n equals 20, the shape becomes more and more like a normal distribution, more symmetric. Also, notice that the graph on the left is more spread out than the graph on the right. So notice as you go from n equals 5 to n equals 10, n equals 20 rather, that the standard deviation goes down. Okay, so as the sample size increases, the standard deviation goes down, and the shape becomes more normal. Okay, so how did the sampling distributions compare? The distribution here looks approximately skewed left, right? Slightly skewed left for n equals 5, but it's roughly symmetric for n equals 20. In fact, it looks like it looks like it's trying to become almost like a normal distribution. But for now, you can see it kind of looks roughly symmetric. So it kind of looks like that right now. But it's roughly symmetric, and that means we can figure out what their mean is. So the center for the one on the left is around. If you go here, it's probably around here, because the mean is not going to be at the peak because it's skewed left. It's going to be slightly pulled to the left. So it's going to be around 2002. Okay. This will be approximately where the mean of that lies. This is just an approximation. All right. So mu x is approximately 2002. Um, and notice that around here, it's also around 2002 because it's in the middle. So the mean of a symmetric curve is around the middle. And so it appears that the middle is also around 2002. Okay, so notice that they both have the same um, mean, but they have different variability, right? So if you look at the distribution on the left, is more spread out or variable than the one on the right. In fact, if you were to put a number, this right here, if that's the variability from there to there, right, from there to there, then how many of those will actually fit? Well, from there to there, it looks like we were to kind of estimate it, it looks like it's almost about 2 times, right? It's almost like this is 2 times as spread out as the one on the left, okay? So, or as the one on the right. So, in other words, the one on the right is about half as variable as the one on the left, and hence a decreased sigma. All right, so the next thing we're going to look at is the idea of the mean of the sampling distribution. Okay, so notice that the mean of the sampling distribution is still going to be the same regardless of the sample size, but that the variance or the variability is going to, the standard deviation is going to decrease as you increase the sample size. That's an important concept. And the mean of the sampling distribution is actually going to be just the mean of the population distribution. They're one and the same. Okay, so that's important. And however, the standard deviation, as we saw, decreases with sample size, and therefore it's not just going to be the population standard deviation, it's going to be the population standard deviation divided by the square root of n. Okay, and so notice that as n goes up, then sigma x goes down, right? Sigma x bar goes down. Okay, so that's important to realize because n is in the denominator. Now remember this standard deviation formula only applies as long as a 10% condition applies, which is that the sample size is less than 10% of the population. Okay, this has always been the case, even for proportions. It was the same case. All right. Now the sigma x bar, what it does, if you were to interpret it, it measures the typical distance or the average distance between a sample mean x bar and its population mean mu. Okay, so the typical distance between those two things is what that refers to. All right. So now let's look at a couple more things here. So the sample mean x bar, notice because of this formula, this is by definition an unbiased estimator. Okay, so let's recall what an unbiased estimator is. So recall that an unbiased estimator is one that whose distribution, whose mean of the distribution of its distribution, so the mu of the statistic is actually equal to the parameter that you're trying to measure. So if you recall, when we did the proportions, we said that the mu p hat, the p hat was a statistic, so the average of that distribution, the sampling distribution, was equal to the parameter p. That's just an example, okay? Now in the example that we're doing today, it's mu x bar is the statistic and mu is the parameter, okay? That's a very important concept. So the variability of x bar depends on the variability in sigma and of the sample size, as we saw with that formula. So notice that multiplying the sample size by 4 actually is going to cut the standard deviation in half. Let's show you why that's the case. Okay, so we said that sigma x bar is equal to sigma over square root of n, right? And so what we're going to do is we're going to replace that n with 4n. So we're going to make the sample size 4 times as large. And then if we did that, well, what's the square root of 4? Well, the square root of 4 is 2, right? So we have sigma over 2 times the square root of n, which is the same thing as 1/2 sigma over square root of n. And there you go. So notice it cuts it in half, right? Similarly, if I multiplied the n by 9 or 9n instead of 4n, well then the square root of 9 is 3. So if I multiply the sample size by 9, it's going to cut the standard deviation by a third. Okay? Hopefully that makes sense. All right, so example 1. The number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies with a standard deviation of 15.8 movies. Suppose we take a random sample of 100 students from the school and calculate x bar equals the mean number of movies viewed by the members of the sample. Identify the mean of the sampling distribution. So remember we said that it's an unbiased estimator, so the mu of the statistic x bar is equal to the parameter, which is the population mean mu. So they're identical. So that means that it's going to be 19.3 movies, right? All right, and then part B, calculate and interpret the standard deviation of the sampling distribution. So we're going to do the standard deviation, but we're going to first verify the 10% condition is met. So since we took a random sample of 100 students and it's from a large high school, we're going to assume that 100 is less than 10% of the population of all students at the large high school. we're going to assume that that's the case, in which case it passes the 10% condition. And so then we can use the formula sigma over square root of n, which the sigma is 15.8 movies, and it was out of 100. So 15.8 out of the square root of 100. The square root of 100 is 10, so it becomes 15.8 divided by 10, which is 1.58. Yeah, 1.58 movies. All right, so then we'll interpret this in simple random size. So if we want to interpret the standard deviation, remember we said it's the typical distance from the sample mean, or the sample mean and then the population mean. So in simple random sizes of size 100, the sample mean, which is x bar, right? The sample mean viewed of number of movies viewed will typically vary. So there's a typical distance from x bar to the mean. It will vary about how much? Well, about 1.58, right? So it varies about 1.58 movies from the mean, which is 19.3, right? From the true mean, right? The true mean is the mu of 19.3 movies. All right, pause the video and see if you can do part A. All right, I'm going to go ahead and pause the video, see if you can do part B. All right, so let's look at the problems here. So David's iPod has about 10,000 songs. The distribution of the playtimes for these songs is heavily skewed to the right, with a mean of 225 seconds. Now he's got a 10,000 songs here, so that's interesting enough. He's got a standard deviation as a standard deviation 60. Suppose we choose a simple random sample of 10 songs from the population and calculate the mean playtime. All right, identify the mean. Okay, so the mean mu x bar is equal to mu, which is equal to the 225 seconds, right? Right. So there's that. And then we'll go to part B. It says calculate this, interpret the standard deviation of the sample distribution of x bar. So we're going to assume that the 100 was it 100 or is it 10 songs? It's 10 songs. I'm sorry. This is a should say 10 songs, right? If I go back to it, sample size of 10 songs, yeah, is from the population. Okay, so we're going to assume that the 10 songs is less than 100 or less than 10%, sorry, of all songs in David's iPod. But we can actually calculate this, right? So 10 out of 1,000, notice, is equal to 1%, right? Which is less than 10%. All right, so that's true. So that checks it. And now sigma x bar is sigma over square root of n, so it's 60, or yeah, 60 was the sigma, right? Double check there, because I don't remember exactly. Oops. Standard deviation of, yeah, it was 60 seconds, okay? So 60 over square root of 10, which that's going to give you 18.974. Okay. All right. Interpret in the simple random sizes of sample size 100, the sample mean number of movie or number this should say play times, sample mean play times. This is a copy and paste from the previous one. That's incorrect. Viewed will typically vary by about should say seconds. 18.974 seconds from the true mean of what was it? True mean? It was 225 seconds. Okay, so there's a typo there. All right, there you go. All right, so let's look at the next learning target, which is learning target 2. How to explain how the shape of the sampling distribution of x bar is affected by the shape of the population distribution and the sample size. Okay, so there's an important theorem known as the central limit theorem. Okay, this is probably this is a really important theorem, one of the most important. And and it says that if I take a simple random size from any population, regardless of the shape of the population, the distribution, with a mean of mu and standard deviation sigma, it says that as long as n is sufficiently large, then what we could say, okay, so as long as n is sufficiently large, and what we mean by large, the cutoff is when n is greater than or equal to 30. Okay, that's our cutoff. So 30 or higher. If that's true, if n is sufficiently large, then the sampling distribution of the sample mean x bar is necessarily going to be approximately normal. So you see in the graphic above, you have the original population, which happens to be normally distributed, but notice it doesn't have to be normally distributed. As long as the sample size is greater than or equal to 30, the sampling distribution is going to be also normal, okay, approximately. But notice that it's skinnier, it's smaller, right? It's lower variability. So that's because of the fact that sigma x bar is equal to sigma over square root of n, if you recall, right? And so if I have a sample size, then it's going to decrease the variability. So that's why. But the mean of them is the same. Notice that the mean of both distributions is the same, and the mean of is just mu, right? Okay, so let's look at some key points here. If the population distribution is normal, then so is the sampling distribution of x bar by default. Okay? This means that no matter what the sample size is, as long as this is normal, the population is normal, then this is going to guarantee to be normal, right? Regardless of the sample size, no matter what the sample size is. Okay? But then what about this sample size of 30 then? Well, that is guaranteed. That guarantees that no matter what the shape of the population is, the sampling distribution will be normal, approximately. And even if the population looked, silly, like that or something like that, if the sample size is greater than or equal to 30, then it's gonna still be it's gonna be approximately normal. Okay, so if the population is not normal, then the sampling distribution of sample means will be approximately normal as long as the sample size is sufficiently large, right? Or which is n is greater than or equal to 30 in most cases. If the sample size is small, though, however, and the population is not normal, then that means it's not guaranteed that the sampling distribution will be normal, right? However, the sampling distribution will approach normality even though it doesn't have full normality, right? So it'll still retain some characteristics. It'll try to approach normality while retaining some characteristics of the population. So, for example, if the population were largely skewed to the right, this is the population, and the sample size is small, then the sampling distribution will approach normality, but it'll still be slightly skewed to the right. Okay, so this one's large skewness, and this one is lower skewness. So notice it's trying to approach, and I don't know if I did that graphic any justice, but it's trying to approach normality, but it's still slightly skewed to the right. Okay? Hopefully that makes sense. So the skewness, it'll still retain some of its skewness. All right, so let's look at an example, right? So example 2, the heights of young women follow a normal distribution. So it follow normal distribution with a mean of 64.5 and a standard deviation of 2.5. If one were to find probability that the randomly selected young woman is taller than 65 inches, 66.5 inches, answer the following questions and label the axis under the distribution. All right, so is the population, is this distribution right here that they're asking us for, is it the population distribution, the sample distribution, or is it the sampling distribution of sample mean, x bar? Well, they're asking us for the randomly selected young woman being taller than 66.5. So this is an X value, okay? It's not an average of 66.5. It's a specific value, right? It's a specific height. So if X is the height, then this X is going to be greater 66.5. That's the cutoff, right? So X means that we're dealing with the population. If we're dealing with X bar, then that would be the sampling distribution of X bar, right? So this is going to be the population. We're dealing with the population, not with the sampling distribution of X bar. So we're not actually applying the central limit theorem in this problem because we're not dealing with X bar, right? If that makes sense. All right, so the shape of the distribution here of the population is normal because they mentioned that right here. All right, and then it says the value of the mean and the standard deviation. They told us those values as well, right? So it was mu equals 64.5, and then the sigma is 2.5. This is dealing straight with the population. And so we know the population is normal. We can go ahead and label those things. So this is dealing with X, right, which is the height. All right, so we got 64.5 for the mean, and we're going to add the standard deviation to the right and subtract it on the left. 67, 69.5, and then 72 here. We're going 3 standard deviations on the left and on the right, which is typical, is what we do. And 59.5, and then lastly 57. Okay, and we're going to mark where we want the probability to be 64.5 or 66.5. That's what they asked for. I'm going to shade to the right. All right, there you go. So if one were to find the probability that the mean height of a simple random sample of 10 young women exceeds 66.5 inches, answer the following questions. Now, what distribution are we dealing with now? We're talking about the mean height now. So the mean height is X bar, right? So that means we're dealing with the X bar distribution. So sampling distribution of X bar. Okay? And now, is it going to be normal or not? Well, because the population is normal, therefore the sampling distribution is guaranteed to be normal, even though the sample size is 10, which is less than 30, right? That's okay, because the original is normal, therefore, even if we have a small sample size, it's still going to be normal, right? If the population were not normal, then we couldn't say this. All right, so the value of the mean and the standard deviation here is going to be normal, and the mean is the mean x bar, right, mu x bar, which is equal to mu, right, as we mentioned, that mu x bar equals mu in the beginning of the lesson, and it's going to be 64.5, the same exact mean. However, the standard deviation is going to be different, so we have sigma x bar. Remember the formula is sigma over square root of n, and so we get 2.5 over the square root of 10, which is approximately 0.79. Okay. Um, I just want to double check something real quick to see if they gave us. So they gave us the standard deviation up here, so 2.5. So I just to let you know. All right. So let's go ahead and label this graph then. So um, when we label the graph, we're going to we're going to start with the middle, 64.5. Okay. Right, so we got 64.5, and we're gonna add 0.79 to it to get the other numbers. So we got 65.29, 66.08, 66.87. I'm gonna subtract. We got 63.71. 62.92, and 62.13. All right, so now we're going to label the area. So the area was x bar equals 66.5, which is right around here.
And notice that the area is smaller here than it was for here. Here is the area is a lot larger, but because this is a narrower graph, a skinnier graph, because look at the scale, it actually has less values for less extreme values. And so having an extreme value like 56.5, it's going to be a smaller probability of that occurring. Okay? All right, so let's look at, so go ahead and pause the video and see if you can try the check. Okay, scroll down here so you can look at part B. All right, so hopefully you paused it and tried it. So let's take a look at Keith's example. All right, so it says Keith is the manager of an auto care center. Based on service records from the past year, the time and hours that a technician requires to complete a standard oil change and inspection follows a right skew distribution with a mu equals 30 minutes and sigma equals 20 minutes. For a promotion, Keith randomly selects 40 current customers. Okay, so it's got a right skew distribution with mu is 30 and sigma is 20. He has to randomly select 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. He budgets an average of 35 minutes per customer for a technician to complete the work. So if we want to calculate the probability that the average time, that's an X bar, guys, right? Average. It takes to complete the work exceeds 35 minutes, answer the following questions. So because we're doing the probability that the average is greater than 35, right? That's what we're doing. Well, then we're talking about the distribution of X bar, the sampling distribution. Now, does it say whether it's normal or not? Well, it does say that the population is skewed to the right. So if the population is skewed to the right and the sample size is large enough, by the central limit theorem, the distribution of X bar should also be approximately normal. Now, looking here, it says that we have 40 current customers that he selects. And so, therefore, because n equals 40 is greater than or equal to 30, that means it's approximately normal by the central limit theorem. Okay? Even if the population is not normal, the sample distribution of X bar will be approximately. So the value of the mean here is mu X bar, and we said that mu X bar is equal to mu, and mu is equal to 30. Okay? And the standard deviation is sigma X bar, which is equal to sigma over square root of n. And we're going to plug that in here, so it's 20 over square root of 40, which is approximately 3.16. All right, so, and we're going to verify the 10% condition as well, okay? So we can, remember, we can use this formula as long as the 10% condition holds true. If the 10% condition does not hold true, then actually the sigma x bar would actually be less than what is calculated here, okay? So we want to keep that in mind. But most of the time in these problems with AP, it's gonna satisfy that condition so that you can calculate it. All right, so here we got 40 people is less than 10% of all customers. That is very likely, okay? Very reasonable to assume. So it satisfies the 10% condition, therefore we can calculate that. All right, so now let's go and calculate. We got the X bar distribution, so this is 30. Then we're going to add 3.16 to either side on the right and subtract on the left. Okay, and those are the numbers on the right. This is kind of weird the way that looks, so let me just bring that down. All right, so on the left, we're going to subtract. Okay, we got 20.52 for the last one. So X bar is 35. And we're shading to the right. We want the probability that X bar is greater than. Okay, so then what would the shape of the distribution, what would be the shape of the distribution if Keith decided to give away only 10 free oil change? Well, n is 10 is less than 30, so that means it fails the CLT, the large counts condition. So therefore, because it's the population was skewed to the right, then that means that the sampling distribution will also be skewed to the right. Okay, the sample size is small, therefore the sampling distribution is likely to also be skewed to the right. However, it's not going to be as strong as the population, right? It's going to try to approach normality, but not quite be there. So therefore, it's going to be more slightly skewed, or yeah, less skewed to the right. All right. So let's look at learning target 3. So learning target 3, it says, if appropriate, use a normal distribution to calculate the probability involving X bar. So let's start calculating. Now that we established normality for the X bar distribution using the large counts condition, we are now able to do normal distribution calculations. So using the example from the learning target number 2, we can now calculate, do the normal distribution calculations. So first what we're going to do, let's recall what learning target number 2, that example was. So learning target number 2, use this example right here, right? The heights of the young women. And we've established that the shape of the distribution is for part B, or was it for part B? Let me look at it. Yeah, it says the probability that a randomly selected young woman is taller than 66.5, so that's part A, okay? We've established that it's normal. We've drawn the normal distribution. We've marked it. We're finding the area to the right, okay? We've established what the mu and the standard deviation were, so we're going to calculate the z-score for this, okay? And then find the area to the right. And we're going to also do it with the calculator. So, again, I'm just going to draw a sort of rough picture of what we were looking at, just to refresh your memory. Okay. So again, the image or the distribution, the normal distribution, kind of looked like this, where we had 64.5 for the mu, right? So the mu x bar was, or the mu, sorry, was 64.5, and the standard deviation was 2.5. Okay. And we marked 66.5 here, so we're shade to the right. Okay, so that's how it looked like originally, okay, in that example. So let's calculate the z-score. How do we calculate the z-score? Well, remember that the z-score is equal to value minus mean over standard deviation. So in this case, our z-score formula is going to be the value is x. This is the x distribution right here, minus the mean, which is mu, over standard deviation, sigma. Okay? So we're going to be using that formula here. So if we use that, we get 66.5 minus 64.5 over 66.5 is the value, 64.5 is the mean. The standard deviation we said was 2.5. All right, and that's going to be approximately 0.80. When we calculate, it's going to be 0.80. So now the probability that x is greater than 66.5 is equal to the probability that z is greater than 0.80, which that's what we calculated. And we're going to use our table here, the normal distribution table, to calculate this. Remember, the normal distribution table gives you the area to the left. So if I want to find the area to the right, I need to subtract from 1. Okay, so we got to keep that in mind. So we got 0.80, you see that here, and therefore the area is 0.7881. Okay, so that's the area. So we're going to use that. Okay, so 0.7881 is the area to the left, so I got to subtract that from 1. And that gives me 0.2119. And there you go. That's the area that we wanted to look for. So on the calculator, remember, we would use the normal CDF. And we would do the lower limit is 66.5. The upper limit is infinity, so a really big number. So, for example, 1,000 or more. I'll just use 10,000. And then the mean is going to be 64.5. The standard deviation was 2.5. And if we do this, we calculate, we get the similar result, or actually the same result, 0.2119. Right, so part B, find the probability that the mean height of sample random sample of 10 young women exceeds 66.5 inches. Okay, so we want the probability that x bar is 66.5. Mean is x bar. Okay, and we did use that distribution. That was this distribution right here. Okay, so let's go ahead and establish. We established that it was a bell curve like this. It's 64.5 still here, and then we wanted to look at the x bar was 66.5 area to the right, and the mean of this distribution was the same, 64.5. The standard deviation we calculated over here, the sigma over square root of n, we got 0.79. Okay, so we're going to calculate that. So what's the formula for the z-score here? Well, the formula for the z-score, we'll write it over here. Remember, it's value minus mean over standard deviation. So now if I use that formula, the value is x bar, right? The mean is mu x bar. And the standard deviation is sigma x bar. But remember that the mu x bar is equal to mu, and the sigma x bar is equal to sigma over square root of n. Okay? So we're going to use that formula for the z-score for here. Okay? So z is equal to the value, 66.5, minus the mean of 64.5, over the standard deviation, which was 2.5, over the square root of n, which is 10. And that's going to be approximately 2.53 for the z-score. So there you go. We can put that down here. D is greater than 2.53. Let's look that up here. 2.53. So 2.53. So 0.9943. You can see in the table. All right. So we're going to subtract from 1 because we want the area to the right. And we get 0.0057. So then the calculator functionality, normal CDF, the lower limit is again 66.5, and this is your x bar equals that. Your upper is infinity, so let's say 10,000. The mean is 64.5. The standard deviation is 0.79. And if you do that, you get approximately 0.0568, which is very similar to that if we round it. Okay? All right, guys. So I'm going to show you learning target number 2, the check. So this was the check from learning target number 2, right here. Okay, so you can get an idea. So based off of this problem right here, we want to calculate part A, the probability of part A, and then we want to calculate the probability of part B. So pause the video and see if you can try that, the learning, which is this check here. All right, there's part A, this is part B. Okay, so hopefully you tried it. It's good to practice it on your own before checking the solution and getting feedback. So calculate the probability that the average time it takes to complete the work exceeds 35 minutes using the check from learning target number 2. So again, the average time it takes. So we're looking at the probability that x bar is greater than 35, right? And so we're going to convert that into a z-score. But let's again, we're going to be using the z-score formula. So x bar minus mu over sigma over square root of n. Okay, so our x bar is 35. That's our value. Let's actually do the graph. This is x bar. This is the x bar distribution, and it was the average was. I gotta go back to see what it is. So the average we said was. It was. Hold on. Yeah, right here. So the average was 30, and the standard deviation is 3.16. Okay. So the average It's 30. The standard deviation is 3.16. Okay. We got 30 here in the middle, and then we want to be exceeds 35. Shade to the right. Okay, so let's calculate it. So we got the mean, which is 30, or the value minus mean. So the value is 35 minus the mean is 30 over standard deviation over square root of 40. And again, we calculated this to be that already. Okay, so you don't have to do this. So you can just replace that with 3.16, but I'm showing the whole thing. Okay, so let me see. Let me just write it here. So it's 5 over the 3.16, okay, which is approximately 1.58. So that's our z-score. We want the probability that's greater than 1.58. So we got 1.5 right here, and then 8. So then we go down there, go down there. Looks like they both cross right around there. 0.94 to 9429 it appears. Okay. Okay. So got 0.9429. 1 minus 0.9429, which is 0.0571. Now the calculator, you got X bar for the lower, we got 1,000 or whatever, a really big number for infinity for the right side. The mean is 30, standard deviation is 3.16, and you get approximately 0.0568 as well. You can ignore this here. All right, so there's your check for that one, and then we'll do part B. So part B says the average time per customer, or how much average time per customer should Keith budget if he wants to be 99% certain that he doesn't go over budget. Okay, so this is an interesting problem. So what we want to do is we have the let's do the normal distribution. Okay, so we have our normal distribution, and it says how much average time per customer should Keith budget if he wants to be 99% certain that he doesn't go over budget. So he does not want to go over budget, right? According to this. And so what that means is that he wants to go either on time or under budget, right? So that means we're doing the area to the left. That's what he wants, okay? So he wants to be at the time, at the average time, or less, okay? That's what he wants. So we want the area to the left, and that's going to be our X bar. Now, we don't know what that is. That's what we're trying to find. How much average time would it have to be? And we know that the area here has to be 0.99 because he wants to be 99% certain, right? Or 0.9900. I'm gonna put it to 4 decimal places, okay? So 0.99%, I'm gonna convert that to 0.9900, and we're gonna look up the z-score for that, okay? So if we want the area to the left, let's calculate the approximate z-score. So we're going to use our table to look up approximately where the z-score would be for 0.99, an area of 0.9900. So remember, that means we're looking at these numbers here. So 0.9900, that's 0.9875, so we're getting closer, we're getting warmer. 0.9898, 9901, so that looks like to be the closest, guys, right there. 9901, 9898. So this looks to be the closest. So what's the z-score for that? It's 2.3. Continue that over 2.33. So that seems to be my z-score is 2.33, okay? That's the closest z-score, approximately. All right, so that means our z-score is approximately 2.33 for that. And so remember the formula for the z is x bar minus mu over sigma over square root of n, right? Which is just sigma x bar. I'm going to call it sigma x bar. So if I want to solve for x bar, I have to multiply both sides by sigma x bar and then add the mu. I'm going to show you this off to the side, but I will not do the whole thing in the notes, but I'll show you off to the side with the whole process. So if this is z, the formula for z, then what we're going to do is we're going to multiply both sides by sigma x bar. in order to cancel this out. And so we get z sigma x bar equals x bar minus mu. And then we're solving for x bar, so we're going to add mu to both sides. That cancels out. So we get x bar equals z sigma, or mu plus z sigma x bar. Okay? And that's the formula that we're going to use. All right, so we're going to use that. Let's write that formula over here. So x bar equals mu plus z sigma x bar. And that's going to help us find the time, the average time that we need, so it doesn't go over budget. All right, so again, we know what x bar, actually, yeah, so what we're going to do is, yeah, let's just plug in for the z-score formula. We know that z is 2.33. We know that, we don't know x bar, but we know that mu is 30, and standard deviation is 3.16. And so basically we're multiplying both sides by 3.16 to cancel that out, right? And so we end up getting x bar is 30 plus, we're using this formula, basically by solving that, 30 plus 2.33 times 3.16. And we do that, we get about 37.4 minutes. There you go. Let's use a calculator. Now, to use a calculator for this, we're going to be using the inverse norm function, okay? So it's important, that's the inverse norm. And the inverse norm wants you to provide the area to the left, and then the mean and standard deviation. That's it. The area to the left is 0.99, right? So we're going to put that. So 0.99, and then the mean is 30. The standard deviation is 3.16. And if you do this, this will give you approximately 37.35 minutes, which is rounded to what we have when we did it with the z. Okay, there you go, guys. So now let's look at learning target number 4 and 5. Number 4 is calculate the mean and standard deviation of the sampling distribution in not sample proportions, but sample means. And then and interpret the standard deviation. Determine if the sampling distribution is approximately normal. All right. Okay, so and then the 5 is determine if the sampling distribution x bar minus x bar 2 is approximately normal. So now we're switching from just doing x bar to doing 2 x bars, right? And we're doing the difference, x bar 1 minus x bar 2. Okay, so let's look at the formulas and stuff for that. So first off, let's look at the shape. The sampling distribution of x bar 1 minus x bar 2 is going to be approximately normal as long as some conditions apply, which is like the large counts condition. But this time the large counts condition applies to both x bar 1 and x bar 2, right? So both populations. So if both population distributions are normal, then of course the sampling distribution is going to be normal. If, for example, none of them are normal for the original distribution, then the x bar 1 and x bar 2 will be approximately normal if the large counts condition applies. If one of them is the populations are normal and the other population is not, then it's okay. You'd have to have a large enough sample size for the one that was not normal. Okay, so any of these combinations will work. So again, it is approximately normal if both sample sizes are large, assuming that the original distributions are not normal. Then as long as both sample sizes are large, then we're good. If one of the populations is normal distributions and the other sample and the other population is not, then the other sample size has to be large. Okay? All right, so the mean of the sampling distribution, x bar 1 minus x bar 2, is as follows. It's just going to be mu1 minus mu2. That's it. Okay, there's that. And then the standard deviation of x bar 1 minus x bar 2. Remember that to find the standard deviation formula, let me just briefly review that for you. Remember that sigma A minus B, in order to calculate this, remember that standard deviations do not add or subtract. In fact, even if you have a difference, it's not subtraction, it's addition of the standard deviations. Of the, not the standard deviations, it's addition of the variances. So you can only add variances. You can't add the standard deviations in the same way. So we know that the variance of the variable a minus b, we could do that. We could do sigma squared a plus sigma squared b. Okay? That's we can do. And remember that it's addition because even though this is negative, it's being squared, so it's going to be positive anyways, right? It's actually going to be the absolute value, so it doesn't really matter. It's still going to be addition even if we have a difference. So we can add variances like this, and therefore the standard deviation would just be the square root of the variances. Okay? Now in the case of x bar 1 minus x bar 2, we know we can use this formula, and we have sigma squared x bar 1 minus sigma squared x bar 2. But remember that sigma x bar is the sigma over square root of n, right? And so we're going to need to plug that in. So if we do that, we get square root, and then this gets replaced with sigma 1 over, and we can actually, yeah, there's going to be sigma 1 over square root of n1. But then it's squared, right? Because of this, it's a variance. Minus, and then this is going to be just the 2 version. Sigma 2 over square root of n2 squared. There you go. And so notice that we get that the square and the square root cancel, right? But then this is going to be squared. So we get sigma squared 1 over n1 plus sigma squared 2 over n2. And this is your formula for this, okay? So that's how you find it. But you can. This formula is provided on the should be provided on the formula sheet, or in a way you can find it. You can find it. So let's just provide the formula. So no need to memorize it, but you do need to understand how to do transformations because that was in the previous chapter. All right, so there you go. Now remember, this formula only applies as long as the 10% condition applies, is satisfied. And in this case, since you have 2 populations, that means both sample sizes that you take from each of those populations has to be less than 10% of their respective populations. So N1 has to be less than 10% of the big N1, and N2 has to be less than 10% of big N2, the population size of the population number 2. All right, so now, because there's 2 different populations, it's important to realize that that this formula for standard deviation is correct only when we have 2 types of independence, okay? So not only do we need the 10% condition to be able to apply the formula, but the formula itself is correct if we use the 2 types of independence. Because we have 2 populations, right? Population number 1 and population number 2. Well, first off, these populations have to be independent from each other, okay? So the samples that we take have to be independent from them, okay? So if I take a sample, let me actually make this bigger because it's kind of small. Let's do here. This is gonna make it bigger. So here, this is number 1. Then this is number 2. All right. So if we take a sample there and a sample here, those samples have to be independent from each other. Okay. So that's the first part, independent samples. The second part to it is that the observations within the sample itself. Let me actually make this bigger, just so you can see it. Within the sample itself, let's say you have 2 dots on there, and those represent the data. But the data itself, the observations within the sample also have to be independent. So you have 2 types of independence here. I hope that makes sense. within the sample and between the samples of the populations. And so when you're sampling without replacement, the actual value, this is where the 10% condition applies. So the 10% condition applies to independent observations within the sample. So 10% condition applies to that. So when sampling without replacement, the actual value of the standard deviation is less than. Okay, so it's actually less than what the formula suggests if this is not met. All right, so we kind of talked about it. That's a little bit of the detail there. But let's look at what the sigma x bar 1 minus x bar 2 tells us. What's the interpretation? And remember, it's going to tell us how the typical distance from this, right, to the mu 1 minus mu 2. Okay, so it's going to tell us the typical distance from this to that. Okay, like what is that typical distance? So it tells us how much the difference in the sample means will on average vary, will typically vary from the difference in the true means. Difference in the true means. If we repeat the random process, of course, many times. All right. So there's that. That's their interpretation thereof. So let's look at examples. Let's look at an example of that. All right. So example 4, based on the information from the U.S. National Health and Nutrition Examination Survey, the heights of 10-year-old girls can be modeled by a normal distribution with a mean of 56.4 inches and a standard deviation of 2.7 inches. The heights of 10-year-old boys can be modeled by a normal distribution with a mean of mu b equals 55.7 and a standard deviation of that. I forgot to highlight the fact that this is normal for the girls. Suppose we take independent, simple random samples of 12 girls and 8 boys of this age and measure their heights. All right, so lots of information there. Now, what is the shape of the sampling distribution of if I subtract the average height of the girls minus the average height of the boys? Well, it's going to be approximately normal. And the reason being is that both populations are normal. We have normal distribution here, normal distribution there. So, therefore, because both are approximately normal, that means it doesn't matter what the sample size is, still going to be approximately normal. Note, if the population were not normal, then the sample sizes would have to be at least 30. This is just a side note. All right. Okay, so let's to our conclusion. It's approximately normal, and let's find the mean of the distribution. So the mean of x bar g minus x bar b is just going to be mu g minus mu b. And so that's going to be 56.4 minus 55.7. Remember that they gave us those mu's over here, 56.4, 55.7. So they give us it's in the problem. So subtract those, you get 0.7. And that's the mean. Calculate and interpret the standard deviation of the sampling distribution. Verify 10% condition. So let's verify the 10% condition is met. So that means that the sample size for the girls is only 12. And so it's reasonable to assume that it's less than 10% of all 10-year-old girls. Because this is all, girls from the U.S., right? National Health. So that makes sense. And then NB, we have a sample size of 8 boys, and that's reasonable to assume it's less than 10% of all 10-year-old boys. So check for both of those. Therefore, we can use the standard deviation formula. So let's apply it. So it's a square root. The standard deviation for girls was 2.7. For boys is 3.8. Okay, let me just write the formula over here. Square root of sigma squared g over ng plus sigma squared b over n. So we're going to be using that formula here. Okay, so for girls, it was 2.7 squared for the standard deviation. There were 12 girls. Plus the boys is 1.8 for the standard deviation. Square that over 8 boys. So that's going to be approximately 1.55. And so we want to interpret that. So the interpretation is that the difference in the sample means of girls minus boys for the heights, typically varies by about 1.55. And the units for that are, I think it's going to be inches. Yeah, 1.55 inches from um, the true difference in mean heights of 0.7 inches. Okay, so there you go. So I'm going to pause the video, see if you can look at this problem real quick, and then I'm going to switch over to the other page so you can see the problem. So there's this the check here. Okay, and then here's the problems. So you can look at it. So go ahead and pause the video, see if you can try it. All right, so let's look at it. So it says here, a fast food restaurant uses an automated filling machine to pour its soft drinks. It says using different settings for small, medium, and large. When the large setting is chosen, the amount of liquid dispensed follows a normal distribution with a mean of 27 ounces. Okay, so for the large, it's mean of 27, standard deviation 0.8. For the medium, it's also a normal distribution, so they're both normal distributions. The mean is 17 and a standard deviation 0.5. The manager selects independent random sizes of 20 cups filled using the large setting and 25 cups using the medium setting during 1 week. Let X bar L minus X bar M be the difference in the sample mean liquid under the two settings. Okay, so let's go down to the problem. So what is the shape of that distribution? Well, because both distributions were normal, then that means the difference has to be approximately normal. Okay? Because the population distribution is the original for both. Now, part B, find the mean of the sampling distribution. It's just going to be mu L minus mu M, right? For this. And mu L is 27, and mu M for the medium setting was 17 ounces. So this is going to be 10 ounces. Okay? Calculate, interpret the standard deviation. So let's first verify the 10% condition. The large setting, there were 20 cups that were used. That's likely going to be less than 10% of all large cups of soft drinks that they used that week. And in the medium setting, there's only 25, so that's likely also to be 25% or less than 10% of all medium cups of soft drinks that week. So if we assume that, this should say L, by the way, and this should say M, not G and B. But we can calculate the standard deviation of the difference. So remember, it's 0.8 for 0.8 for the standard deviation for the large cup, and it was 0.5 for the standard deviation for the medium cup, so 0.5 squared. And there were 20 cups here and 25 cups there. So if you calculate that, we get about 0.205 ounces. All right, so interpret with the difference in the sample mean amounts of large minus medium liquid typically varies by about 0.205 ounces from the true difference in means in the mean amount of 10 ounces. All right, so let's look at learning target number 6. So, if appropriate, use a normal distribution to calculate probabilities involving x bar 1 minus x bar 2. So now that we establish normality and things like that, where it's approximately normal, we should be able to use normal distribution calculations. So, using example 4 with the girls, right, girls minus boys, we want to find the probability that the difference in the sample mean heights for girls minus boys is at least 2 inches. All right, so if you recall, for that example, let's go back to what it was. So let's go back here in example 5. Hold on a second here. Not example 5. It should be example 4. Here you go. For the boys and girls, we have the mean is, or the mean difference, right, which is the mu x bar, is 0.7. So we're going to use that. And the standard deviation, we said, was 1.55. Okay? So we're going to go ahead and apply that here. So the mean is 0.7. And then the standard deviation, again, we said it goes by the 1.55. So let's add that. So it's going to be 2.25. Next one is 3.8. And then we got 5.35. And then if I subtract it, I get negative numbers. Negative 0.85, negative 2.4, and negative 3.95. So we want the probability that it's at least 2 inches. So 2 inches or higher. So that's this difference of girl minus boy for the average height is 2. And we want to do at least. So at least means we're going to shade to the right. Okay? And that's how the distribution looks like with the shaded areas and all that. And let's continue that in order to calculate the z. Okay, so for this part right here, we're going to show you what the formula would be for calculating this. Okay, so in order to calculate this, we need to show you, we need to recall that z is value minus mean divided by standard deviation, right? Okay, so and so that means that the value, now what is the value? Well, the value is x bar g minus x bar b, right? That's the value. And so, okay, so let's write that out. Let's just write the general formula. So x bar 1 minus x bar 2 is the value. The mean is mu x bar 1 minus x bar 2, right? Over the standard deviation, which is sigma x bar 1 minus x bar 2. But as we know, that mu x bar 1 minus x bar 2 is simply mu 1 minus mu 2, right? So we're going to replace that with mu 1 minus mu 2. Okay, just to kind of show you. And that's the formula we're going to use for the z-score. Now, what is x bar 1 minus x bar 2? That's the x bar girl minus x bar boy, which we established was 2 in our graph, right? It has to be at least 2. And the mean, we've established from the previous example that the mean was 0.7. We calculated it right here. Okay. So let me just write down that this girl minus boy, this is 0.7, and then we said that the standard deviation for boy minus girl is approximately 1.55. Okay, so let's subtract that. So 2 minus 0.7 over 1.55, and then it's approximately equal to 0.84. All right, and then by the way, we don't need this part. We don't need this here. We're gonna get rid of that because we're only wanting to do one value. And so probability that x bar girl minus x bar boy is greater than or equal to 2, which is the same thing as z being 0.84. Let us look up the 0.84. So 0.84 is right here. You got 0.8 and 4. So there's our area, 0.7995. Okay, 7995. So let's put that here. So, but that's the area to the right. So if I want the area to the left, I just got to subtract from 0.7995. And I get an area of, I'll just do it over here, of 0.2005. If I use the calculator functionality, it's going to be 2 at the left, the lower area, infinity, or a really big number for the right area, and then there's your mean and standard deviation. Okay. So we said 2, then like a big number like 1,000, 0.7 for the mean, 1.55 for the standard deviation, and we get an area of 0.2008, very similar to 0.2005. All right, folks, go ahead and pause the problem and see if you can do the soft drink example. I'll show you the example over here in case you need the the details. So here are the details for that problem. And here are the details for the check. All right, so hopefully you tried it and looked at the information and gave it a shot. So, right, let's go ahead and label this. So we got, this is going to be, we said that the mean for this was 10 in the previous problem, and that the standard deviation is about 0.205. Okay, and so there you go. So in the middle we got 10. Then we're going to go by 0.205. So 10.205, 10.410, and then 10.615, and then we'll do it on the left side as well. All right, and then so now it says they wanted to do it within 0.25 ounces of the true difference of means. So that means if the true difference is 10, within means you have to add or subtract 0.25, right? So that means it wants to be between, if I subtract that, it would be 9.75. If I, so it wants to be between that and if I add it, 10.25. Okay, so it wants to be between those two values. So 9.75 is like around here. This is the difference in the sample mean. So x bar 1 minus x bar 2, x bar L, sorry. I'm just going to write the numbers. 9.75 and then 10.25. All right, so we want that the difference is between, within, right? Within it means between. Okay, so again, we want this to be between 9.75 and 10.25. And so we're going to need to calculate two z-scores, all right? So let's calculate the first z-score. So the first z-score is going to be, remember, it's going to be the values 9.75 minus the mean of 10 over the standard deviation of 0.205. And for the second z-score is the value is 10.25 minus the mean of 10 over the standard deviation of 0.205. Okay. Right, so if we do that, we get a z-score of approximately negative 1.22, and then here is approximately positive 1.22. All right, so that's what we get, and now we're going to put that here. And so now we can look up the values in the table. So if we go to the table, we're going to look up both negative 1.22 and positive 1.22, and then subtract those values. So we got 1.22. That value is 0.88. Okay, so we'll write that here. Minus, then we're going to look up for negative 1.22. The negatives should be over here. Yeah, so negative 1.22. Negative 1.22, which is 0.1112. Okay. We'll subtract those. All right, so 0.1112. And there you go. So then we get our area of 0.7776 for the probability. Okay, and then if we do this on the calculator, we should get a similar result. The lower is 9.75, the upper is 10.25, the mean is 10, the standard deviation is 0.205. And we'll show you this calculation on the graphing calculator. All right, so here's the graphing calculator. So we're going to hit second and then vars, and then we're going to go to normal CDF right there, option number 2. Let's see. Yeah, option number 2. We're going to hit that. And then we're going to change we're going to type in, we're going to go ahead and type in the numbers. So we got 9.75, and we got 10.25. The mean is 10, and standard deviation is 0.205. Okay, going to go ahead and figure out the area. So we get about 0.7774. Okay, so we'll write that down. Pretty similar to what we got there. All right, guys, that's going to do it for the video. Hope you found this useful and informative. And as usual, I'll see you in the next one.